Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. The next topic we are going to learn is sequential logic. In the last few videos, you came across combinational circuits. Those circuits had some inputs which were represented as binary data and it was processed using the logic gates such as AND, OR, NAND, etc. And you got some output in terms of these binary values after the processing. Basically, these combinational circuits were built using the logic gates which processed the input to form the output. That is, the output of these circuits always depended on the input values. Or in short, the inputs of the combinational circuits decide their output at any point of time. Let's have a look at the picture that shows the block diagram of the combinational circuit. Here the input X is processed by the logic gate inside the combinational circuit to form the output Z, or we can say that Z is a function of input X, that is Z is equal to f of x. And hence it is very clear that the input variables are deciding the output variables in the case of combinational circuits. Sequential circuits work slightly in a different manner. They are often characterized by the presence of a memory element in their circuit. So, what is this memory element here and why do we need that? Suppose while you are processing the input variables, you want to know what their previous value or the state was. If you want to know the previous value, then you need to store it somewhere. If you have to store it somewhere, then you need to have memory or storage. And the sequential circuits uses the previous state during its processing. This is why we are using memory in the sequential circuit. So, actually the memory element differentiates a sequential circuit from a combinational circuit. Let us see the inside of a sequential circuit now. It contains a combinational circuit to which the memory is connected. The inputs and the memory elements together determine the output of state of the circuit. Look at the picture. This is the block diagram of a sequential circuit. You can see the memory elements are like a feedback to the combinational circuit. Here, the output of the sequential circuit Z is decided by the external input A and the present state of memory element Y shown in the picture as the small letter y. There is one more output, let us call it as internal output Y. It is capital Y and it forms the present state of the memory element which will be treated as an input along with the external inputs in the next cycle. So, for a sequential circuit there are two inputs, the external inputs and the present state of memory. And there are two outputs, one is external and the other output is applied to change the present state of the memory element to the next state. Before moving into the details of the sequential circuit, let us see where they are used and applied. Since these circuits have memory elements, they are used in places where the previous state is considered as significant. For example, it is used while counting. When you are counting, you always need to remember what the previous number was. Since these sequential circuits have memory elements, they are able to do this and hence they are used in places where the previous state needs to be considered. One good example in practical life where the sequential circuit is used is the automatic counter, which counts the vacant slots in the car parking area. See in the picture, when a car is parked, it increments its value by 1 and when that slot is vacant, the value decreases by 1. It is also used in digital clocks and moreover all computers use the sequential circuits for processing. The practical applications of sequential circuits are vast and varied. They are used to build flip-flops, counters, clocks, shift registers and registers used in microprocessor, state machines in finite state automata, etc. Now, let us move on to the types of sequential circuits. There are two types of sequential circuits, synchronous and asynchronous. Have you heard these terms before, the synchronous and asynchronous? What is the difference between them? Literally, the word synchronous means happening at the same time or occurring at the same time, whereas asynchronous is the opposite. It is not happening at the same time. So, understand that these terms have something to do with the time. Now, let us see how these terms are applied in the context of sequential circuits. The synchronous circuits use triggered clock pulses at discrete intervals of time to change the memory element. Triggering means you are making something happen in the circuit, or in other words, we are controlling the circuit using certain signals. And here we use clock pulses to trigger the circuits. Now, what are clock pulses? They are signals with changes in the voltage occurring at regular intervals. Since the circuits use clock pulses for triggering, they are also called as clocked sequential circuits. Asynchronous sequential circuits does not depend on a clock pulse to change their state. They are governed by their inputs itself. Now, let us see the differences between these two. Since there are no clock pulses used, asynchronous are faster than synchronous, but asynchronous circuits are difficult to design compared to the synchronous circuits. Synchronous circuits are more stable and predictable because the changes happens at discrete and regular intervals of time. But in the case of asynchronous circuits, the changes can occur at any point of time, as it is purely dependent on the inputs alone. The memory elements used in synchronous are clocked flip-flops, and in asynchronous are unclocked flip-flops or time delaying elements. We will learn about these new terms in detail soon. So, let us revise the points. A synchronous circuit easier to design, asynchronous difficult to design. Synchronous circuit is slower, asynchronous is faster. Synchronous circuits triggered by clock pulse, asynchronous not triggered by clock pulse, but any change of inputs affect them. In synchronous, the changes happens at discrete intervals. In asynchronous, the changes happens at any point of time. In synchronous, memory elements are clocked flip-flops, and in asynchronous, memory elements are unclocked flip-flops or time delaying elements. Now, look at this picture. There is no clock pulse for asynchronous, whereas the synchronous is triggered by the clock pulses. Hope you have got the basic idea of sequential circuits. Now, let us move on to the next. You have come across a new term, flip-flop. Let us learn about flip-flops. What are they? They are the memory elements that are used in the clocked sequential circuits, and they are capable of storing one bit of information. Remember, it can store only one bit of information. What are their inputs and outputs? They will take a binary value as an input, and on the trigger of a clock pulse, it will store the value. It has two outputs, one is the value stored in the flip-flop and other one is the complement of that value. Now, let me introduce one more term here, the latches. What are latches? They are the flip-flops without a clock signal. Please see the picture. You can make out that the latch is missing the trigger. There is no clock pulse for latches, but there is a clock pulse for flip-flop. Please note that the clock pulse is denoted as CLK in the block diagrams. The pictorial representation is an arrow with a filled triangle head that differentiates the clock pulses from other inputs. So, we are emphasizing the point that the circuits which uses clock pulses are synchronous and clocked flip-flops are used to build those circuits, and those are not triggered by the clock pulses are asynchronous, and flip-flops without clock signals or the latches are used to build the asynchronous circuits. Now, you are ready to dive into the deeper levels. We will start with the latches. First, we will learn SR latches. The SR latch has two inputs, S and R. S stands for set and R stands for reset. They have two outputs, Q and Q complement, which are complements of each other, and is used to store a single binary digit, either 1 or 0. Basically, the universal gates such as NAND and NOR gates are used to build the flip-flops and the latches. You might have come across the NAND and NOR when you learnt about the logic gates. NAND is formed after negating the output of AND gate, and the NOR gate is formed after negating the output of OR gate. See the picture, the OR and NOT is clubbed to form the NOR, and 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 NOT is clubbed to form the NAND gate. Why are they called as universal gates? It is because NAND and NOR gates can be used to build all the other basic logic gates such as AND, OR, NOT. They can also build any combinational circuits made up of the basic logic gates. This feature makes the NAND and NOR gates as the universal gates. Now, let us see the design of a basic SR latch using NAND and NOR. We will discuss the design using NAND gates first. They have two NAND gates, two external inputs S and R, and two outputs Q and Q complement. The design of the circuit is in such a way that the two outputs of the latch are always complements of each other. That is, when Q is equal to 1, then Q complement equal to 0, and vice versa. Look at the input of the circuit. You can notice that the output of one gate is cross coupled with the input of the other gate. Why is it done so? In sequential circuit, we are considering the previous state of the circuit while processing the value for the current state, and this way of cross coupling will help us to obtain the previous state of the circuit. These values are fed back into the circuits as internal inputs, or in short, this forms the feedback path. That's how the latches preserves the memory and uses it for the next cycle of processing. To understand the working of SR latch, let us make use of the truth table. You have learnt in previous videos that the truth tables gives you the clear picture of various combination of inputs and their corresponding outputs. When there are n inputs, a truth table should have normally 2 raised to n combinations of input. Here there are 2 inputs, so we have 2 square, that is for combinations of inputs. But in the truth table given, there are 5 entries. There is a repeated combination of input. We will see how each combination of input results in the output and why a particular combination is repeated. To understand the working of SR latch, you should recall that a NAND gate produces 1 when any of their inputs or both their inputs are 0, and it produces 0 only when both their inputs are 1. Let us have a quick look at the NAND gate's truth table. Here the last row alone produces 0 because its both inputs are 1 and the rest all produce a 1 because they have at least 1 0 in their output. Let us go back to SR latch. To start with, let us assume that S equal to 1 and R equal to 0. To learn the working of latches and flip-flops using NAND gate, an effective tip is consider the input which is 0 first. Here R equal to 0. So, we will consider the R gate first. Then as per the truth table, the output of that NAND gate should be 1 and hence Q complement should be 1. Here the R gate has 2 inputs, one is R and the other is the previous state value of Q. Since the external input R is already 0, you do not have to think about the other input. Why? Because for a NAND gate, if any of its input is 0, the output is going to be 1, and hence you can ignore the previous state value in this case. Now, if Q complement is 1 and the external input S is given to us already and it is 1, then what should be the value of Q? It should be 0 as per the truth table of the NAND gate, because both of its inputs are 1. The Q and Q complement have values now. The next part is a verification process. The condition of the latch is that its each output should be a complement of each other, and let us check whether it is valid in our case. Yes, it is, because Q and Q complement have values 0 and 1 respectively. This state is given in the first row of the truth table. Let us check the third row of the truth table. What if S equal to 0 and R is equal to 1? Here the input S is 0, so let us consider that first. As per the truth table of NAND gate, if S equal to 0, then Q should be 1, and we do not have to bother about the other input Q complement, then which is the previous state value in this case. And if Q is 1 and R, which is the external input, that is already 1, then as per the truth table of NAND gate, Q complement should be 0. Now let us check the condition of complements. This satisfies the condition of complements because Q equal to 1 and Q complement equal to 0. What if both S and R are 1? You have noticed that in the truth table, this combination S equal to 1 and R equal to 1 is repeated. Their outputs are based on a condition. Why is it so? In this case, to determine the present state of the circuit, we need to know the previous state of Q and Q complement, because both the external inputs are 1. Since external inputs are 1, we have to consider the second input to the NAND gate to decide the output. In earlier two scenarios, such a situation was not encountered because any one of the external input was 0. In such cases, it was easy to find out the output by just focusing the external input, which was 0 first. So, how to determine the behavior of SR latch when both inputs are high or when they are 1? Here we will consider the previous states of Q and Q complement. There will be two different contexts, that is when Q equal to 0 and Q complement equal to 1, or when Q equal to 1 and Q complement equal to 0. Let us see the first context. When Q is 0, then Q complement must be 1. If Q is 0, then the OR gate has inputs 1 and 0, which will produce an output 1 at Q complement as per the working of NAND gate. If Q complement is 1 and then the input gate S, which is coupled with Q complement, will produce 0 for Q, because both of its inputs are 1 and hence the output is 0. So, you got Q as 0 and Q complement as 1. In effect, the value of Q remained as 0 in the previous state and current state. So, does it indicate that if both inputs are high or when they are at 1, will the latch continue to remain in the same state? Let us verify this by setting the previous state of Q as 1. Then Q complement will be 0. If Q complement is 0, then the S gate coupled with Q complement will produce an output 1 at Q, then definitely the OR gate, which is coupled with Q, will be 0 because its both inputs are 1 now. So, the outputs are Q equal to 1 and Q complement equal to 0, which tells that Q still remained in the previous state 1. So, what does this indicate? When both inputs are 1, then Q and Q complement will continue to remain in their same state. That is, there is no difference between the present and the next state or between the previous and the current state, or we can say that the value is latched or locked. Check out the second row of the truth table. It relies on the previous value of Q and Q complement. So, if in the previous state S equal to 0 and R equal to 1, and if S and R are 1 in the next cycle, Q remains to be 0 itself. Now see the fourth row of the truth table. Here the previous state of Q and Q complement was 1 and 0 respectively, and it continued to remain the same when inputs S and R are 1. So, this is a special case in the working of SR latch, that is, when S and R are high, no change happens to the state of the latch. Let us see the last combination. What if S and R are 0? As per the truth table of NAND, if any of its input is 0, then their output is going to be 1. We do not have to consider the previous states in this case, because one of the input here, the external inputs for both the gates are 0. So, if S and R are 0, then the output Q and Q complement will turn to be 1. This violates the condition of the latch that the outputs should be the complement of each other. Here it is not, they are the same, not the complement. We can infer that setting S and R as 0 produces Q and Q complement as 1, which are not the complement of each other, and such a state should be avoided in the operation of latches. So, the last row of the truth table of SR latch points out an unfavorable or undesirable condition. So, care is ensured that such a state should not be happening in its working. Hope you are clear with the construction of SR latch using NAND gate. So, to wrap up, this session introduced a new concept known as sequential circuits, its characteristics, its applications, etc. We also discussed the types of sequential circuits, how they differ, and the building blocks of these types of circuits, etc. Then we discussed two more important concepts, flip-flops and latches. Next, we saw the construction of SR latch, which are used in building the synchronous sequential circuits. That's it for the time being. Hope to see you in the next session. Thank you.